A very good morning, ladies and gentlemen. Here's Group 10, and we are here to present our group project Vapor Compression Cycle for KNC 1052 Engineering Programming and also KNC 1073 Thermodynamic 1. In our Group 10, we consist of four group members, which is Elton Lau Daiting, our team leader, Karen Dam Yiching, Yi Sheng Yu, and also me, Nicole Ting Ensi. So our project aims to explore and analyze the thermodynamic properties and performance metric of our system, which is the vapor compression system, throughout the use of TS plot, which is the temperature entropy plots, and also the PV plots, which is the pressure volume plots. And our objective is to prove and plot the TS graph and also the PV graph by using MATLAB, and also to calculate the coefficient of performance, which is the C or P for our system. So now let us go to the system description for our project. So the vapor compression cycle is a fundamental process used in air conditioning and refrigeration system to transfer heat from a low temperature environment to a high temperature environment. So R134A is a medium that frequently used in the air conditioning and refrigeration system, which aims to absorb and remove heat from the space being cold and then release it. So now I would like to explain our vapor compression system. So this diagram shows the vapor compression cycle, which consists of four main components, which is the evaporator, compressor, condenser, and also our expansion valve. So let's start from the first stage, which is stage 4 to stage 1 for evaporator. So in this stage, it is in an isobaric heat addition condition, which means that the pressure is constant, and it absorbs heat from the core reservoir, which is Q cold. And how we calculate the Q code? We calculate the Q code by using enthalpy from stage 1 minus the enthalpy from stage 4, which is H1 minus H4. Okay, so next we'll go for the compressor stage. So the compressor stage is from stage 1 to stage 2, and in this stage it is in an adiabatic compression condition, which means that our Q loss or Q gain is equal to constant, entropy is equal to constant, and the way for us to calculate the work inlet is equal to H2, which is the enthalpy from the stage 2 minus the enthalpy from stage 1. H2 minus H1. And next we'll go for the condenser, which is from stage 2 to stage 3. So the condenser is in an isobaric heat rejection condition, which means that the pressure is also equal to the constant, and it releases heat to the hot reservoir, Q hot, and the Q hot is calculated by using H3 enthalpy from stage 3 minus enthalpy from stage 2, and it will end a negative value because we reject this heat. And last but not least, which is our expansion valve. So the expansion valve is from stage 3 to stage 4, and it is in an asymptotic expansion condition, which means H4 is equal to H3. And the pressure and the temperature in the expansion valve will drop. Now, let us welcome Elton to present the method in conducting our project.
Hello everyone, I'm Elton. Now I'm going to talk about how we model the vapor compression system. For your better understanding, I already put a graph below here where it represents the temperature and entropy change of refrigerants when they pass through the vapor compression system. So first thing first, we need to identify point 1 as the refrigerants that exceed the evaporator at T1. T1 means temperature 1. So we assume it to be saturated vapor, so that it is easier for us to calculate other thermodynamic properties like entropy and enthalpy. So from point 1 to point 2 is actually a isentropic compression process where the refrigerants in the vapor form, it will pass through a compressor, and the compressor will exert work done on it and heat it until T2. At T2, which is a temperature at point 2, is a superheated temperature. From the point 2 to point 3 is actually a isobaric cooling process, and the condensation process will occur at around T3, which is 345 degrees Celsius in this case. So from the so at point 3, all refrigerants will turn into liquid state and exit the condenser. From point 3 to point 4, isentalpic expansion process will occur, and it will turn the refrigerants from the liquid form into a liquid and vapor mixture. So at point 4, a refrigerant with a liquid and gas mixture, it will enter the evaporator and it will absorb the heat and return to point 1. Now I will talk about the formula that will be used to model the system. So first thing first is mass flow rate equal to power supply to the compressor over work done by the compressor. So in this case, work done is equal to H2 minus H1, and the unit of the work done is joule per kg, while the unit of power supply is joule per second. So the next formula is QC equal H1 minus H4. QC is a heat that absorbed throughout the evaporator. And the next one is QH equal H2 minus H3. QH is heat release throughout the condenser. And this one is in unit of joule per kg. And the last one is the omega equal QC over W, where omega is coefficient of performance, QC is heat absorbed throughout the evaporator, and W is work done by the compressor.
Hello everyone, I'm Yi Yu, and now I will explain about the coding implementation in this project. Firstly, we create the GUI. By the coding showing here, this line create the main figure window by using the code FIG for the GUI with the name of Vapor Compression System and its specific position. Next, we add the input field by using the code showing here. This line creates the UI components such as text prompts by using the coding UI label and numeric inputs by using the UI edit field. For the evaporator temperature, condenser temperature, compressor power, and also superheat temperature with their specific position in the GUI. The next one is the run button. The button is used to plot the cycle. The coding showing here will create a button that when pressed it will call the plot cycle function with the current value of the input field, and the button is created by using the coding UI button. The next one is the result labels. The coding showing here will create a label for the result with a specific positions. After that is the plot axis. The coding showing here will plot the axis for the TS diagram and also the PH diagram. The ASTX in this coding means that the axis for the TS diagram And also for AXPH means the assets for the pH diagram. The coding showing here will create the assets component by using UI6 to display the TS diagram and also pH diagram at a specific position, and set their title by using coding title, and also set their assets label by using S label and also Y label. After we create the assets for the graph, we will create a text area for the display result. The coding showing here will create a text area by using the coding UI text area, which named the results and also specific its position. The next one is the input validation. Before we proceed to the calculation, we need to ensure that all of the input is valid. The coding showing here is the input validation, which will ensure that all the numeric input such as evaporator temperature input, condenser temperature input, power input, superheated temperature input are valid before proceeding to the calculation. It will check for the num value and display an error alert if the input are invalid by using the coding UI alert. It will also ensure that the evaporator temperature must be less than condenser temperature, and also the compressor power must greater than 0. Before we proceed to the calculation, we also need to import the Python Group10 library. The coding showing here is used to import the Python Group10 library. The code calculation of the vapor compression cycle are using the Group10 library via Python integration to get the refrigerant property. Now, let's move to the calculation in this cycle. Firstly, we convert the temperature from degrees Celsius to Kelvin, and we also define the refrigerant in this cycle, which is using the R134A, which is 1112 tetrafluoroethane. And then the prop SI function is used to query thermodynamic property based on a given parameter, which are pressure, enthalpy, entropy, and also temperature. The coding showing here, Q and 1 indicate the querying property for the saturated vapor, and Q stand for the quality, where 1 represent the vapor phase. Q0 indicate the query property for the saturated vapor. Q stand for quality, where 0 stand for liquid phase. After we doing the calculation, we need to display the result. The coding showing here will display the result that we calculated. The lines display the result by using the coding F of the calculation, such as mass flow rate, coefficient of performance, pressure, temperature, enthalpy, and entropy for the each steps in the vapor compression cycle. The coding percentage dot 2f indicate the format of the number with 2 digits after the decimal point. After doing the calculation, we can now plot the graphs. The coding showing here is used to plot the graph. The CAL coding stands for the clear assets and remove all the graphical object from the specific assets, but do not delete the assets themselves. The coding reset is resetting the default value. The whole function allows the multiple plot to be drawn on the same asset without erasing previous plots. The line on the graph are plotted by using the function plot, and the coding negative KO is specified a black line with a circle marker at that point, and the line width 1 set the line width. The coding showing here is used to plot the specific points of each step on the graph. To label the specific point, the x-axis and the y-axis of the specific point are listed out and labeled with number 1, 2, 3, and 4 by using the function labels. The labels are added using a loop function, which is for. Vertical alignment and bottom aligns text label vertically at the bottom of the point, while the horizontal alignment and right Align the text label horizontally to the right of the points. Then the title and the essay are being given specific name. The coding showing just now is used to plot the TS graph, while the PH graph is using the same type of code. And that's all from the coding implementation part.
Next, I will talk about graphical visualization of our system. From point 1 to point 2 is a isentropic compression process. As we can see, the entropy remain constant while the pressure increase from point 1 to point 2. From point 2 to point 3 is a isobaric cooling process. As you can see the figure 2 here, the pressure from point 2 to point 3 remain unchanged while the entropy from point 2 to point 3 decrease because most of the most of the vapor will turn into liquid. From point 3 to point 4 is a isentropic expansion process. As you can see, the figure 2 here, the enthalpy remain unchanged while the pressure decrease from point 3 to point 4. And lastly, from point 4 to point 1 is a evaporation process where the temperature is constant. Now I will talk about how to use user interface. First thing first, we need to input evaporator temperature, condenser temperature, power supply to compressor, and finally the superheated temperature. In this case, we need to take note that the condenser temperature should always higher than evaporator temperature. After that, we click plot cycle and there will be two graphs will be formed. The left hand side is the temperature against entropy diagram, while the right hand side is pressure against enthalpy diagram. So lastly, it will show a result diagram. In the result diagram, we can see the mass flow rate of the system, coefficient of performance, and the thermodynamic properties of each point, include pressure, temperature, enthalpy, and entropy.
Hi everyone, so now I will explain the result. We have put some data into the simulation. For evaporator temperature, we put 30 degrees Celsius, 70 degrees Celsius for condenser temperature, 100 kilowatt for compressor power, and 100 degrees Celsius for superheat temperature. After the input data have put, and these two graphs has been plotted, which is TS diagram and PH diagram, which point 1 is evaporator outlet, point 2 is compressor outlet, point 3 is condenser outlet, and point 4 is evaporator inlet. The result of mass flow rate and coefficient of performance has been calculated here. And the pressure, temperature, enthalpy, and entropy for each point has been shown here. So from point 1 to point 2, it saw isentropic compression, while from point 2 to point 3, it shows isobaric heat rejection in the condenser. And from point 3 to point 4, it saw isenthalpic expansion, while from point 4 to point 1, it saw isobaric heat absorption. In a conclusion, the estimation of the vapor compression cycle with the given input parameters provide valuable insights into the performance and behavior of the refrigeration system. The mass flow rate and COP are crucial indicators of the system capacity and efficiency, while the stat points and thermodynamic diagram offer a deeper understanding of the cycle dynamics. The result indicates that the system is operational and moderately efficient with a COP of 2.32. However, there's room for optimization. Potential improvement could include enhancing the compressor efficiency, reducing thermal losses, and selecting an optimal refrigerant. By focusing on this area, it is possible to increase the COP and overall system performance. In conclusion, this stimulation serves as a powerful tool for engineers and researchers to design, analyze, and optimize vapor compression systems for various applications. It provides a foundation for further exploration and refinement, ultimately leading to more efficient and effective refrigeration solutions.